Hello, we are the DIBS team, which stands for Drone In-Flight Battery Swap, and our project presentation is as follows. So just to lay the foundation for what our project actually is, we aim to address the problem of limitations that drones have with respect to the range, distance, and length of time for which they can be operated. So our design approach to help address this issue is to essentially develop a mechatronic system which allows drones to swap batteries mid-flight. Now, this comes in the form of four different phases, we could say. The first of which is drone communication and navigation. So essentially, we're going to have two drones in our project, both a mission drone and an auxiliary drone. The mission drone will be performing some sort of task, and it'll have to send a low battery signal to the auxiliary drone. The auxiliary drone will then be user-controlled and navigated to the in-air mission drone, which will then lead to the second phase, which is after rendezvous, the drones will then have to align themselves for the battery swap, and that will happen via image processing. This will feature cameras, colored tape, and some degree of autonomy. Now, the next phase is the actual full-on battery exchange, which involves the auxiliary drone dropping a new battery into the mission drone, and the mission drone then going underneath, the auxiliary drone then going underneath the mission drone to catch the battery from the mission drone. In doing so, the mission drone will have to properly position a new battery to continue its flight, which involves the fourth phase, which is uninterrupted power. This involves seamless power supply, which is paramount to the operation, and this is going to be essential in order to avoid reboot, loss of data, and complete failure.
So I would like to now give you an overall mechanical design overview of how this mechanism will work. So what you're seeing right now is the core of the drone. So this is going to be what's mounted on the mission drone. The rotors and the mechanism for flight is excluded for clarity here. But what we basically have is we have a basket that catches the battery from the auxiliary drone, and then you have a cover plate that moves back and forth throughout the battery into one of two battery housings. And the reason we have two battery housings here is so as you can see, when we drop the first battery in, we don't want to lose power, right? So we want to have two batteries at the same time for just a short amount of time. That way, when we drop the battery that has been discharged from the mission drone, we still have power running at all times on the mission drone. And what you see here on the left picture here is the battery case. In the battery case, what we have is just the battery inside like some sort of 3D printed case, keeps it safe from the elements. It keeps it safe from when it falls or when it impacts the mission drone, so nothing breaks. And overall, it keeps the system seamlessly working. In the middle picture here, you have the copper leads that are going to be outside on each battery case. As soon as the battery hits the bottom of the mission drone and bottoms out, it'll automatically be connected with the mission drone electrically through these copper leads. And then on the far right picture, what you have here is the battery linkages that control when the battery can and cannot be dropped. So when you can open one of either linkage to drop the battery when you're ready. So when the auxiliary drone is underneath the mission drone, you simply rotate one of the linkages, the battery drops out.
Now, in order to make this battery swap occur, one of the most important electrical components that we're going to need in our system is the hot swap integrated circuit. Given that the battery swap will be occurring mid-air, we cannot afford to disconnect the initial battery and then reconnect the new battery. This would result in the drone computer needing to reboot and would also result in stalling and a potential crash. Consequently, the hot swap system will allow us to keep two batteries connected at once, safely, prevent any reboots, and retain flight data and maintain mission status. An example of the integrated circuit that we want to implement into our mission drone is on the left.
As you can see, this is our schedule. So far, we've completed phase 1 and almost the entirety of phase 2. Our next step is going to be the alpha prototyping phase, as well as purchasing the bulk of what we need. And this is going to lead us into the actual funding, which, as you can see on this slide, we do get some funding from our school, but we are going to need at least an additional $1,000, which is why we're requesting $1,000 from you today. Thank you for your time, and I would hope that you consider joining us and sponsoring the DIBS team.